Hey everyone! In this video, we're going to be taking a look at some of the possibilities for when a function does not have a derivative. So what I'd like to do is we'll take a look at some of the possibilities, we'll sketch them out, we'll talk about each of them, and then we'll take a look at a specific example where we're going to determine whether or not a function has a derivative at a specific x value. So to start off with, here are some of the possibilities where this happens. So the first one is if a function has a sharp corner. So an example of a function that has a corner is the function y is equal to the absolute value of x. So let me graph this function. And if we take a look at the graph of the absolute value, we can see that at 0, we have this sharp corner. Now, the reason the derivative doesn't exist at the corner is because as we approach from the left and the right, the slopes of the tangent lines are different. Coming from the left, the slope of my graph is equal to -1, and therefore the slope of all those tangent lines is also -1. Coming from the right-hand side, my graph has a slope of +1, and same idea. The slopes of all the tangent lines have a slope of +1. So because the slopes of those two tangent lines are different as we're approaching 0, the derivative doesn't exist. A second example is if my graph has a vertical tangent line. A function that has a vertical tangent line is the cubed root of x, which looks like this. So at the x value 0, this graph has a vertical tangent line. Now, the reason that this is happening is as I come from the left and the right, the slopes of my tangent lines are increasing without bound. So if you can imagine, as I come from the right-hand side, if I start farther away from 0, my tangent line is pretty flat. But as I approach 0, that tangent line is getting steeper and steeper. And as I get really close to 0, the slope of that tangent line is going to increase without bound. Now the same thing happens as I come from the left-hand side. So it starts off relatively flat, and then as we move closer to 0, the slope is increasing, and it's approaching positive infinity. Well here, because as I'm approaching from both sides, the slopes of those tangent lines are both approaching positive infinity, we end up with this vertical tangent line. And because they're unbounded, the derivative doesn't exist. The last possibility I want to take a look at is if the function has a cusp. An example of a function with a cusp is y is equal to x to the 2/3 power, which looks like this. So this graph also has a pretty sharp corner, but it's a little bit different than the absolute value. In this case, we also have a vertical tangent line at 0, but the difference here is now as I approach from the left and from the right, the slopes of the tangent lines from one side is approaching positive infinity, and as I come from the other, they're approaching negative infinity. So for this example, as I approach from the left, the slopes of the tangent lines are getting steeper and steeper in the negative direction. So the slopes are unbounded towards negative infinity. As I approach from the right-hand side, same idea, they're starting off pretty flat, but as we move closer to 0, they're getting steeper and steeper in the positive direction, so it's approaching positive infinity. So a cusp happens when, as we approach a value, the slopes are our tangent lines, one is positive infinity, one is negative infinity. So in each case, as I approach a value from the left and from the right, the slopes of my tangent lines are approaching positive infinity, negative infinity, or they're approaching different numbers. So what that means is it's not enough to take a look at the derivative. So remember, one way we can define the derivative of a function is the limit as x approaches c of f of x minus f of c all over x minus c. Well, I can't just look at the limit overall. I need to take a look at the one-sided limits. So we need to take a look at the limit as we approach c from the left, and we also need to take a look at the limit as we approach c from the right. If we look at these one-sided limits and they approach the same value, then the derivative exists. But if we look at these limits and they're approaching positive or negative infinity, or they're approaching different numbers, then the derivative does not exist at that value of c. So now that we have this established, let's take a look at a specific example. So here I have a piecewise function, and we want to determine if the derivative exists at the x value of 1. And that x value is actually where my piecewise function switches. So we need to take a look at our one-sided limits. So let's do the limit as x approaches 1 from the left. We'll start with this. Because we're approaching from the left, that means we're going to be using the top piece of our function, because that's the one that matches up with all the x values that are less than 1. So then the way we can find our derivative, f of x minus f of c, which in this case is 1, and this is over x minus c, which is 1. So if we plug in what we have, so we got the limits as x approaches 1 from the left, that top function, negative 2x squared plus 4, and then we're going to subtract f of 1. So if I plug in 1 to this top piece, that's going to be negative 2 plus 4, so that's a positive 2. And then in the denominator, we got x minus 1. Simplifying a little bit, we still have our limit. And 4 minus 2, the numerator is going to simplify to negative 2x squared plus 2. All right, so now we want to evaluate this. I cannot just plug in 1, so we're going to have to simplify a little bit. In the numerator, we can factor out a negative 2. So let's do that. We have our limit, and factoring out a negative 2, we're left with x squared minus 1. So we're left with the difference of perfect squares, which can be factored. So if I continue factoring the numerator, we end up with negative 2 times x plus 1 times x minus 1, and this is all over x minus 1. So that works out for us because now we have this common factor that will simplify. So the x minus 1 will cancel out. And then all we're left with for our limit is negative 2 times x plus 1. And now we can evaluate this by just plugging in 1. So we end up with negative 2 times 1 plus 1. So we get negative 4. So that means as I'm approaching from the left-hand side, the slope of my tangent line is approaching negative 4. We need to do the same thing for the right-hand side. So now let's take a look at the limit as x approaches 1 from the right. And in this case, because we're approaching from the right, we're going to use the second equation, because that's the one that matches up with all the x values greater than or equal to 1. So again, we have f of x minus f of c, which is 1, and then over x minus 1. So now plugging in that second function, so we have our limit that will come over. We have x squared plus 1, and I'm going to subtract f of 1. So if we plug in 1 plus 1 is 2. And then in the denominator, x minus 1. Simplifying the numerator, we end up with x squared minus 1 over x minus 1. And again, we have the difference of perfect squares in the numerator, so let's factor that. And we should have something that cancels out again. So going through, coming from the right-hand side, we end up with a limit that is equal to 2. So that means that the slopes of my tangent lines coming from the left is negative 4. The slopes of the tangent lines coming from the right is positive 2. And because these numbers are different, that means that this derivative does not exist. So to rephrase that, the limit as we approach from the left does not equal the limit as we approach from the right. So that means that the derivative doesn't exist. If we take a look at the graph of this piecewise function, we can see that at this x value of 1, we do have a sharp corner. So that does make sense with what we talked about in the beginning of the video, where the derivative doesn't exist.